Hi everyone. My name is Yaniv. I'm an assistant professor of economics at Carleton College, but I've been doing a lot of deep learning recently, and so some of it brought me into the medical data realm. In particular, I've been doing variational autoencoders. So these are algorithms that reduce the dimension of data in a nonlinear way using a deep learning network. And what you're seeing right now is, for example, a variational autoencoder that's being ran on Cynthia data. So Cynthia data has been mentioned. It's a synthetic data set that aims to mimic real patients and the conditions that they have and how those evolve over their lifetimes. And so the project that brought me here was this one, where I'm trying to use Cynthia data, and I'm trying to reduce the dimension of it. So basically, you can imagine each patient as a vector of zeros and ones, and the zeros and ones say whether the patient had a condition or didn't have a condition. So for example, so patients are vectors of zeros and ones, and the zeros and ones say the condition. And then the dimension reduction, what it does is, instead of having the dimension being the number of conditions, it aims to encode all that vector into just one number. And so that's what you're seeing here. This is like the range of that number. The number can span between -3 and 3. This is the distribution of people on that number. So there's some numbers that are more likely. There are basically like groups of people. And then you could ask the neural network to also explain what this number actually means. And what this number means is presented here as yellow and blue. Blue means basically a 0. There's no probability that that type of patient has that condition, and yellow means that that type of patient has that condition. And that creates for us sort of like a clustering of conditions. We can see what conditions come together, but in essence, it's a way of compressing all that data into ideal types. So you have patients that are, basically you would say, you would tell me that the patient is a -0.9, and I will know, -0.9. I know what this type, what is the general type of -0.9. I know what it means. Okay, because all these conditions co-occur together. So anyway, that's the project that got me here, but that's not the project I want to present to you. One of the this is sort of the broader research agenda. The more particular one is how do we quantify whether a variation autoencoder does a good job? And for that, we need some downstream tasks to actually use the encoding. And so I've been working on this more simple task, where all we're trying to do is we're trying to predict for a patient, given their conditions this year, what conditions will they have next year. So this is a fairly simple deep learning task. So the data source here is Cynthia, but it turns out that Cynthia is not interesting enough. We need to actually, in order to get like the machine learning going, we need to actually run on real people's data. So I've been working with Ed, which is also on the call, and on his side, he can run it on actual real patients' data, and we can see some output from that. So that's what I want to demo for you. I want to demo for you this neural network that we can get, not neural network, sorry, network of which condition creates which condition in the future. And what could be some possible use cases? We can add medication to the vector of features, and then you could ask whether, adding a medication to a particular patient would change the probability of future conditions. This is like doing the experiments, but only using real patient data and large scale, because claims data allows us to do this kind of thing. Anyway, so I'm going to demo the beautiful graph that comes out of it. And I would say that my major contribution here is that I'm not just doing deep learning, but I'm also repeating it enough times that I can generate actual statistics. And so I can say whether one condition causes another condition in a statistically significant way. So I'm using both deep learning here, and I'm using like traditional statistics. So for example, so what you're seeing here now is basically the result of these regressions, right? We are using this is from real patient data, conditions from the whole of 2019. How do they predict conditions in 2020? So, so this is real data, and the edges are like the coefficients in this regression. So if you had shortness of breath in 2019, there's a higher probability, particularly around 1.4%, that you would have chronic obstructive pulmonary disease in 2020. And by having, I mean you would have an encounter with a physician where that's the diagnosis that you're getting. And so you get this wonderful, wonderful network of conditions, which I can just browse all day. You know, for example, if here's an interesting one: body mass index BMI 40 to 44, 45 actually, creates sleep apnea in the next year with a probability of 1% more, and that's statistically significant. So this is like a publishable result, which you can get just from looking at the claims data. Anyway, that's my.
This
yeah.
is freaking amazing. I haven't seen the graph. I know I've seen the grids, but I haven't seen you do this yet. I think there's a ton of applications, frankly, simply in the clinical space all over, because now this is almost, you can do a Bayesian network from this, right? Because you have the prior probability, and the event hits, and you can recalculate the next probability for each member. You can come up with a person and say, for this person, given where they are, here are their risks for next year in a dashboard, right?
That's exactly where this is going.